Physics 2212, Lab 3, Circuits. The purpose of this experiment is to use the concepts of conservation of energy and charge to predict and model the behavior of circuits containing resistors and capacitors. This lab uses a simulation with resistors, capacitors, batteries, ammeters, and voltmeters to model the behavior of an ideal circuit. This lab uses some fundamental physics concepts, including the conservation of energy and charge, the node and loop rules, steady-state circuits, Ohm's law, resistors and capacitors in series and in parallel, resistance and capacitance, and the time dependence of RC circuits. The model used in this lab is an ideal model of a circuit through an online simulation including ideal resistors, capacitors, voltmeters, and ammeters. Some assumptions made for this experiment were that the resistances of the wires and ammeters are negligible. The resistors used are ohmic resistors, and the total change in potential difference for a round trip in a circuit is 0 volts. The system is the circuit and the surroundings are everything else. In this first part, a circuit was constructed with 2 batteries, 2 ammeters, and 2 resistors of different resistances. I predicted that the current in both ammeters will be equal because the circuit is in steady state. This prediction held true. Using the loop rule, the current can be calculated as delta V minus IR1 minus IR2 is equal to 0. With 2 resistors of 47 and 100 ohms and 2 batteries, each of 1.5 volts, the current running through the wires is 0.02 amps. If one of the ammeters is connected backward, it will read negative 0.02 amps because the current will be flowing the opposite way through the ammeter. When one ammeter is replaced by a voltmeter, delta V is equal to 3 volts and the current is 0 amps because this is an open circuit. Therefore, there is no current flowing and the potential difference across the opening is equal to that of the batteries. To find the potential difference across each segment, the voltmeter was attached with one end at the start and end of each segment. From A to B, the difference is 3 volts. From B to C, it's 0. C to D, it's negative 0.96 volts. From D to E, it's 0 volts. From E to F, it's negative 2.04 volts. And lastly, from F to G and G to H, it's 0 volts. When all the segments' differences are added up, the total potential difference for the round trip is equal to 0. This satisfies the loop rule. When the voltmeter is connected, the ammeter will still read 0.02 amps because the voltmeter has a very high resistance, so a negligible amount of current flows through it, leaving the circuit unaltered by its presence. This is a graph of the potential in the circuit relative to the position. The potential increases with the battery as the battery produces an EMF. In all portions of the wire, potential and electric field does not change. The potential decreases with both resistors. There is a steeper decrease for the 100 ohm resistor because its resistance is greater than that of the other resistor. When the ammeter is connected in parallel with the 100 ohm resistor, the ammeter reading increases to 0.06 amps because the resistor is in parallel. By the node rule, the current splits, so less of it is affected by the 100 ohm resistor. This increases the current running through the ammeter. Using Ohm's law and the new current readings, the new resistance of each resistor was found. The first resistor now has resistance of 48 ohms and the second has resistance of 102 ohms. Now, one 9-volt battery is connected to a 10 ohm resistor and a 0.2 farad capacitor in series. When the circuit is connected, the bulb begins to shine bright before going out. Here, the capacitor is charging. The current starts at a maximum and then decreases to 0. When the battery is removed, the bulb follows the same behavior. The capacitor acts as a battery as it discharges. The time for the capacitor to charge and discharge when connected in series with a 10 ohm resistor is 11 and 11.7 seconds. And the times for the capacitor to charge and discharge for the 20 ohm resistor are 18 and 23.4 seconds. In Part 3, the time dependence of RC circuits was observed. For a 9-volt battery, a 200 millifarad capacitor, and a 30-ohm light bulb, the potential difference was recorded at about 1-second intervals after the circuit was connected. The graph of the natural log of the potential at the given time divided by the starting potential was then calculated for each data point. This was then graphed against time, which yields a linear trend according to the equation in the middle of the slide. From the recorded and graphed data, their experimental RC was calculated. The slope of the graph is equal to negative 1 over RC, so the observed RC is 6.05 seconds. The expected RC can be calculated by multiplying the resistance of the resistor by the capacitance of the capacitor, which comes out to be 6 seconds. This is pretty close to the experimental value. Since the computer simulation is an ideal model of a circuit, there should be no discrepancies in the data caused by the model used. Therefore, there should be no error caused by the model, although possible human error can still remain while collecting times for charging and discharging of the capacitor. The ideal simulated ammeter has a resistance of 0, which ensures the displayed value is the full current running through the specific point. A real ammeter, though, will have some sort of resistance. Although this may be low, this would affect the circuit, as readings by the ammeter would cause the current running through the point to be lower than it was in the ideal circuit. With the ideal simulated circuit, the capacitor reaches full charge quickly because there is no resistance in the wires. In reality, it would take some more time for the capacitor to reach full charge because wires will have some resistance.